In this video, we're going to discuss advanced classes. So, one thing we first have to talk about is the interface of a class. An interface defines and standardizes the way in which things such as people and systems interact with another. So, for example, a radio controls serves an interface between the radio's users and its internal components. The controls allow users to perform a limited set of operations such as changing the station, adjusting the volume, etc. Various radios may implement these operations differently. Some may have push buttons, some dials, etc. The interface specifies what operation a radio permits users to perform, but doesn't specify how they are implemented inside the radio. The interface of a class describes what services a class's clients can use and how to request those services, but not how they're implemented. A class's public interface consists of the class's public member functions known as methods. You can specify a class's interface by writing a class definition that lists only the class member's function prototypes and the class's data members. So what we'll do here is we separate the interface from the implementation. So we have a header file .h where the class is defined and a source code file .cpp in which the class member functions are implemented. The benefits it makes the class reusable, and the clients of the class know what member functions the class provides and how to call them. The clients do not know how the functions are implemented, however. So here's an example. We've got this counter class. In counter.h, we do this pragma once to stop a file from being included more than once. Define a constant. And here we define our class. We've got an integer private member, and we have public methods count, reset, and get count. And then in the implementation, we actually implement these methods. Now notice here we've got the counter and the scope operator. What this basically says is we're implementing counter that's defined here in the header file. We're implementing it here. Now, notice we also do include the actual counter.h file. And if you don't implement it here, you'll get an error message unless you implement it here. So basically, this lets us separate the interface from the implementation. So here, in our code, we just include counter.h and just use it. If the reason the header contains the fields and not the method implementations is we need to know the field sizes for the compiler to determine the size of the object. Whereas with methods, only one copy is actually created per class. So, pragma once prevents the class from being defined multiple times if there are any type of multiple inclusion. That is, we include header file x, which includes header file y.h, which includes x.h. In older C++ programs, you might see pound if end-def header name and defined header name, your code, and then an end-if. This uses the C process to exclude duplicate code. It's a matter of preference, but many programmers prefer pragma. In the implementation, each member function's name is preceded by the class name and the scope resolution operator. This ties them to the now separate class definition. Counter : tells the compiler that each member function is within the counter scope and its name is known to other class members. Without counter : these functions would not be recognized as part of the counter class. Instead, it would consider them global functions, and you can't access counters' inner workings. So, method count checks every count to make sure it doesn't exceed our maximum. Obviously, this is a contrived example. If the value is outside of its range, count throws an out-of-range exception. And this notifies the client code that an invalid argument was received. You can use try-catch to catch exceptions and attempt to recover. The throw statement creates a new object of type out of range, immediately terminates count, and returns the exception to the code that attempted to set the counter. If a member function is defined in the class's body, the compiler attempts to inline calls to the member functions. This means you don't implement it separately. In some cases, the compiler will compile this to more efficient code. Only do this with very simple member functions because changes to the header require full recompiling. New programmers must think that objects must be quite large because they contain data members and functions, but that's only true from a logical perspective. Physically, the members of a class are only implemented once for all instances. Only the data is unique. So, the diagram on the right shows how compiling and linking works. So a class's interface and implementation will be created and compiled by one programmer and used by a separate programmer who implements code that uses the class. The client code programmer isn't given the CPP file, just the project file, so the client remains unaware of how the class's member functions are implemented. The client code programmer needs to know only the class's interface to use the class and must be able to link to the object code. Since the interface of the class is part of the class definition, the client code programmer must also have access to the header file and include it. When the client code is compiled, the compiler uses the class definition to ensure the main function creates and manipulates the object of the class correctly. So, to create the executable application, the last step is to link them. The object code for the main function, the object code for the class's member implementations, and the standard template library object code for the classes. The linker's output is the executable application that the user can execute. Compilers and IDEs typically invoke the linker for you after compiling your code. So if you compile code that takes 2 or more source files in Visual Studio, I'll add all the headers and source files to the project and then just build and run. For new C++, open a shell, change the directory, and then you'd list out the files. star.cpp for all C++ files, and then give it an executable name. For REPL IT, just add all the headers and source files, and then just hit run. So, a class's data members and methods belong to that class's scope. Non-member functions are defined in the global scope. Within a class's scope, class members are immediately accessible by all of that class's member functions and can be referenced by name. Outside of a class's scope, public members are referenced through one of the reference methods on an object name, a reference to an object, or a pointer to that object. So, dot and arrow member selectors. You can use the object's name or a reference to the object followed by the dot member selection operator. To reference an object member via pointer, you use the arrow member operator. So, if we have account, we'd say an account ref and an account pointer, we would access them as follows. Account.setBalance, account ref.setBalance, and account pointer arrow setBalance. So, you can overload constructors and delegating constructors. Given a class, we can define multiple overloaded constructors. We can define overloaded constructors with the following properties. For example, if we had a time class, it uses default time, hours, minutes, and seconds, etc. Time would use default just default minute and second. This would default just minute, just second, and this would default nothing. C++ allows constructors to call other constructors in the same class. This is known as a delegating constructor. It delegates work to another constructor. The first 3 of the 4 time constructors can be implemented as a delegating constructor. For example, with time, we can say in the definition, call time with all zeros. Similarly here, we can time with 2 zeros. And finally here, time with the hour and the minute in just 1 zero. So now we move on to destructors. The name of the destructor is a tilde followed by the class name. And it's where the class cleans up after itself when it goes out of scope. When an object is destroyed, it gets called implicitly. The destructor does not actually release the object's memory. It performs termination housekeeping before the object memory is reclaimed. So the memory may be reused to hold new objects, but it doesn't actually let go of the memory. It receives no parameters and returns no values, may not specify a return type, not even void. A class has one and only one destructor, and it must be public. If you don't define one, the compiler creates an empty one. The name of the When are constructors and destructors called? Both are called implicitly often. The order in which these functions called occurs depending on the order in which execution enters and leaves the scopes, where the objects are instantiated. Generally, destructor calls are made in the reverse order of the corresponding constructor calls. Global and static objects can alter the order in which destructors are called. Constructors are called for objects defined in global scope, also called global namespace scope, before any other function in that program begins execution. The corresponding destructors are called when main terminates. Function exit forces a program to terminate immediately and doesn't execute the destructors. Abort forms similar to exit but forces the code to terminate immediately without allowing the programmer to find clean code to be called. Constructors and destructors for non-static local objects are called each time execution enters and leaves the scope of the object. Destructors are not called for non-static local objects if the program terminates with a call to exit or abort. So, the constructor for a static local object is called only once when execution first reaches the point where the object is defined. The corresponding destructor is called when main terminates or the program calls function exit. Global and static objects are destroyed in the reverse order of what they're created. Destructors are not called for static objects if the program terminates with a call to abort. So we're going to demonstrate when constructors and destructors are called. So, code here. All right, so here, we're going to establish a class called create and destroy, which is nothing but have a constructor and a destructor and a couple pieces of data. Okay, and then we're going to implement the two, which basically involves outputting them and outputting when things run. So for our main object, what we're going to do is we're going to create an object and then create and destroy an object again. And then we will call a create method, which creates and destroys an additional object, and so forth. So when we run it, we see that the object 2 is constructed first, then 3. Option 1 is constructed first because it's global. Local and main and static and main are run next. Local and create is run next, and same with static and object 7. Then, when we finish the function, we're going to destroy the two of the objects that got created in there. We don't destroy the static one because it hangs around. Then we destroy then we run the fourth constructor, and then when the main function ends, we start calling the destructors in reverse order of creation. And we close off the two locals in main. We control get rid of the statics in create and then in main, and finally the destructor, the main destructor for the global. So, a subtle trap: reserving a reference or a pointer to private data members. A reference to an object is an alias for the object's name. It may be used in the last line of an assignment statement. A member function can return a reference to a private data member. If the reference return type is declared const, the reference is a non-modifiable L value and cannot be used to modify the data. If it's not const, a subtle error is going to occur. A reference return may make a call to that method, bad set hour, an alias for private data members. The method call can be used in any way that the private data member can be. So don't do that. Protect your data members. The assignment operator can be used to assign an object to another object of the same type. By default, such assignment is performed by Memberwise assignment, also called copy assignment. Each data member of the object on the right is assigned individually to the same data member on the left. However, when you use it with a class that has pointers, things don't work quite like you think. We'll come back to that. Objects may be passed as function arguments and may be returned from functions. Such passing and returning is performed using pass by value by default. A copy of the object is passed or returned. C++ creates a new object and uses a copy constructor to copy the original object's values into the new object. For each class, the compiler provides a default copy constructor that copies each member. Copy constructors, however, have problems with pointers, and so we might have to customize them. Some objects need to be modifiable and some do not. You may use keyword const to specify that an object is not modifiable, and that any attempt to modify the object should result in a compilation error. So here we define time as a const, and it's possible that in say both const and non-const for same classes, C++ disallows method calls for const objects unless the methods themselves are const. That controls side effects. This is true even for get methods that do not modify the object. That's why we declare as const all methods that do not modify the object on which they're called. A constructor must be allowed to modify an object so the object can actually be used and be initialized. A destructor must be able to perform its termination housekeeping before it cleans up. And attempting to declare a constructor or destructor const will be a compilation error. So, you can have objects as members of other classes. So, an alarm clock object needs to know when it's supposed to sound an alarm, so we can include a time object as a member. This is called composition and is sometimes referred to as a has-a relationship. A class can have objects of other classes as members. So, let's look at a demo. Alright, so here we have our main, which just calls our functions in, we define a couple classes, address and employee. Here we're going to create an address and set up its values, and then we're going to pass that address into an employee so it stores it there. And then we can output it calling the toString method. And so here is an address. We basically set up a constructor where we read in all the values, have properties to get to all the actual, have methods to get to all the actual values that are in getter methods, and then a toString method that nicely output things. Similarly for employee, we have that, but one of our parameters is an address. The other thing I've done here is show that you could pass in the parts of an address and build your address as well. So the overloaded constructors. And anyway, here are all the IDs for set and get. And when you pass it in, you can pass in a whole address object. And employee.h is just the definition, same with address.h. And our main program is actually what calls things. So what happens when you don't use the member initialization list? If a member object is not initialized through a member initialization, the member object's default constructor will be implicitly called. Values established by the default constructor are overridden by set functions. So there's also this idea of a friend function. A friend function is a non-member function that has the right to access the public and non-public class members. This is kind of a unique thing to C++. Standalone functions, entire classes, or member functions of other classes may be declared to be friends of another class. So to declare a friend, the function, we place the keyword prototype in the class definition and precede it with the keyword friend. To declare all member functions of a class 2 as friends of class 1, place a declaration of the form friend class 2 in class 1. The friend declaration can appear anywhere in a class and are not expected by private and public modifiers. So, friendship is granted, not taken. For class B to be a friend of A must say, I want B to be my friend. It's not symmetric either. If you're a friend of A is a friend of B is not a friend of A, and there's no transitive. If A is a friend of B and B is a friend of C, A is not a friend of C. And we have a friend demo, which I completely misspelled here. And here we do is we've got our main and our address object, and in our address.h we declare friendly output as a friend to address, and here we can call friendly output and send in an address, and then inside the implementation of friendly output we can actually look at the member variables. So that's kind of nice as a way to sneak around data encapsulation. So you can specify overloaded functions as friends of a class. Each function intended to be a friend must be declared in the class definition as a friend of the class, like everything else. So every object has access to its own address through a special pointer called this. This pointer is not a part of the object. It's just a reference. The memory occupied by this pointer is not reflected in the result of sizing. Rather, this pointer is passed by the compiler as an implicit argument to each of the object's non-static member functions. It's passed in and it's hidden. So, why do we use this? Sometimes we have name collisions. Member functions use the this pointer implicitly or explicitly to refer to an object. An explicit use of this pointer is to avoid naming conflicts. Member functions use the this pointer implicitly or explicitly to reference a member's data, members, and other functions. A common explicit use of this is to avoid naming conflicts between a class's member and the member function parameters. So the type of this parameter is a pointer to the object it's in. In a non-const member function, the this pointer has the type employee, for example, it's an employee pointer, constant employee to a constant pointer to a non-constant employee. In a const member function, this type has employee const, a constant pointer to a constant employee. Implicit and explicit using this pointer to access the object's data member. Let's look at another demo. All right, so here we've got main, and we're going to define a simple test class, test here, and we're going to implement it. And then in print, we're going to say here, this arrow X is the this is this object you're currently running in, and it should print the appropriate info. This is the object you're currently pointing to. That's all there is to it. So another way to use this is to enable cascading function calls. So invoking a multiple function sequentially is in the same statement we can do by having a member function return the contents of the this pointer. So you create a function, pointer type f, which returns the contents of this, and then you can use that to call the next item in the chain, which from the object returned. Basically, your first call returns the object it's working on, and your second call uses that first response. By the way, this shouldn't be pointer type; it should just be type. You can repeat this as many times as you need. In certain cases, only one copy of a variable should be shared by all objects of the class. This is called a static data member and used for these and other reasons. Such a variable, remember, represents a class-wide piece of information that is data that is shared across all instances and not specific to any one object of the class. Static data members have class scope. A static data member must be initialized exactly once, and fundamental type static data members are initialized by default to 0. In C11, all static constant data members can have initialized in-class syntax. So I've thrown a lot at you, but hopefully you've been able to follow it, and I will see you next video.